Welcome back. Here is a video on parallel circuits. Okay, so parallel circuits are different from a series circuit in that there is more than one path. There are multiple paths, or branches, we might say, for the electrons to travel. And on each branch, there is exactly one component, or one resistor. Okay? We'll later talk about circuits where there could be multiple components on a branch with different branches, and that's kind of like having a little series circuit within the parallel system. But right now we're going to focus on strictly parallel, which is exactly one component or resistor per branch. Okay? So like our series, we've got some relationships. We have some interrelationships. These are unique to a parallel circuit. These interrelationships are true for both the series and the parallel. So these should look the same. We've got Ohm's law again, that volts is still equal to the product of current and resistance, and we've still got our power formula. Power and measured in watts is the same, or is equivalent to current times voltage. If we look at our interrelationships though, these are different. And you can think about like the plumbing example, again, the analogy. This is our water tower, and think of water being supplied to maybe your house, my house, and another neighbor's house, if we're all living on the same street next door to each other. And so this water tower is creating water pressure and then the flow. We might turn our faucet on when you have yours off. And when I turn my faucet on, I've got running water here. There is flow of water, and a lot of it's going down the drain and kind of heading back through the city system, right? And you might have yours off. So I can have current flowing here, but not here. Some of the water, though, might head down the street and not go through my system, but go through my neighbor's system. Okay, the total current, the total amount of flow in a parallel system is equal to the sum of how much current flows through each branch. Hopefully that makes sense. The total resistance experienced we'll come back to in just a second. Okay, I'll save that one for later. It looks messy. The total voltage, think of this as pressure, like the water tower supplying pressure to your house and my house and the neighbors. Well, we're all in the same system. We should all have the same amount of water pressure. So that's the same thing here with electricity. We should have the same amount of voltage at each branch. And because there's only one component, one resistor in each branch, remember from a series circuit we had said that the amount of volts that cross a resistor always have to, if we're going across multiple resistors, they have to add up to equal the total voltage. Well, here it's only going to go across one, because then it's going to head, those electrons head right on back to the power source. So the voltage drop across this one resistor for those that take this path have to equal the total volts. And then across here has to equal the total volts. So these are all equal. Okay, in a parallel circuit. So these are different relationships. The total resistance, I know it's hard to kind of summarize in values by looking at this formula, but I'll tell you, the amount of resistance, the total resistance that's experienced relative to how big these are, in the end, the total resistance will be less than any of these individually. These may have different values. Whichever one has the smallest amount of resistance, the total will be smaller yet. So in a parallel system, we reduce the total resistance on our circuit by branching these out and giving the electricity different options and different paths to flow. Okay, so these are our relationships. Now let's do an example. Okay, I set this up the same way we did our series circuit. I set up columns for Ohm's law, volts, current, resistance. I set up rows for all my common things, all volts, all current, all resistance. Notice in my columns, the labels are all the same, all T's, all 1's. So when I'm looking in columns, I know I can use Ohm's law. All right, let's plug in what we know. I see the total volts is given to me. I see the total resistance, I'm sorry, not the total, but the individual resistances are given to me. 100 ohms, 75 ohms, and 85 ohms. And that looks like it. Right? Didn't give you anything else. Okay. So, at first glance, it appears the obvious thing to solve for is the total resistance, because I've got all but one in that row. I don't have anything in this row. I only have one in that row. And then if I look in columns, I don't have any column with two values. So I'm not ready to use Ohm's law anywhere. Now, there is another option though. If we go back to these relationships real quick, the pressure is the same everywhere. So once you have 1 volt, you have all of them. So that's the actual easy one to do right off the bat, is to fill these in. So that's the first thing I did. If you want me to document the order, the first thing I did was used the fact that all the votes are equal. That helped me fill in the rest. Okay. From there, I can use Ohm's law. Right? I've got 3 columns where I have 2 out of the 3. So the second thing is V equals IR for 1, 2, and 3. Can't do it for the totals yet. So let's work that out. Volts equals I times R. Right here, we're going to have 12 volts equals the current unknown times the 100. You're going to divide both sides by 100. And you're going to get 0.12 amps for the current. Repeat here. We've got the volts is 12. The current is unknown. The resistance is 75. We're going to divide both sides by 75. See here, what's 12 divided by 75? 0.16 amps. And lastly, 12 volts is equal to the current times the resistance. So I need 12 divided by 85, right? We would divide both sides by 85. And I will round this. It'll be accurate enough for now. I'm going to go ahead and round it 2 decimal places. So we're going to call that 0.14 amps. That is a rounded value though. Okay. Now I have 2 options. I have 2 rows that are almost completely filled. The only thing missing is the I and the R. Well, fielder's choice. I get to choose. And if I look at the formulas, I think I know which one I want to work with. This one doesn't look so bad with the current. This one down here, yeah, I don't know about that. Tell you what, I'll do it both ways, just so you're not scared off by this. I could use Ohm's law once I figure out the total current. Then I'll have V, total volts, total current, and I can use Ohm's law again. But I'll do both just to show you the work. Okay, so number 3 though, I'm going to start with the current. So total current. Total amount of flow of electricity is how much went through my house, or your house, my house, the neighbor's house, right? So I'm just going to add up all the currents. So we had 12, 16, and 14.14. So we're going to add those up, and I'm going to get 0.42 amps. Now that is a rounded value. Remember, this one got rounded, so it's not exact. So from there, I could do Ohm's law, but let's go ahead and do it the hard way. So I would do this: V T equals I T times RT, or if you're willing to accept the challenge, this. So it's 1 divided by, okay, the entire quantity of it's a sum. This really represents the reciprocal of each of the resistances. So the reciprocal of 100 is 1 over 100. And the reciprocal of 75 is 1 over 75. And the reciprocal of 85 is 1 over 85. Now, with a graphing calculator, I can type kind of all this in, and boom, it just spits it out. I'll break it into smaller steps as if you had a really simple basic calculator, okay? So the worst case scenario, you got to use your calculator and slowly go through it. So If I slowly go through it, 100th is 0.01. 1 over 75 is 0.013 repeating. And 1 divided by 85 is 0.011765. I'm going to take that out a ways. This is the type of formula that you don't want to round too quickly. So I'm going to use my calculator and try to type in as many values as I can. So you're going to want to go ahead and find that sum. I'm going to use that exact value. It's already on my screen, and just hit plus 0.013, and I'll keep hitting a bunch of 3's, plus the 100th 0.01. And so my denominator simplified down to 0.03598, etc. And I want to simplify that, so I'm going to do 1 divided by that value. On my graphing calculator, I've got this answer button here that I can use. It's the second function. If I hit second, here, ANS is the answer. It'll use the previous answer, and it'll just kind of substitute it for me. And so I get 28.49. That was ohms, right? There you go. So 28.49 ohms. Should get about the same thing if I used Ohm's law. It's probably going to be just a little different because remember, this is rounded. That 0.14 was really like 0.1411 something, and so we chopped off those values, and so we really have more decimals here. So we're going to lose a little bit of accuracy based on me rounding here, where here I try to preserve more accuracy and round at the end. Okay, so there you go. There is an example with a parallel circuit. Hopefully that helps. Good luck on doing yours today.